Very good morning and warm welcome to everyone. Salam, we love UPM. My name is Gabriel Bautistuta as your MC for today and on behalf of Smart Farming International Webinar 2020. For your information, this event is organized by Malaysian Society of Agriculture and Food Engineer Student Chapter MSAE-SC. The main objective of this event is to educate participants in agriculture through modern technology and create new perspectives regarding agriculture in our society. It is my pleasure to inform you that we have an outstanding total of 788 participants that have registered with us yesterday. It is also our privilege to have you on board, and thank you for joining us. Before we move on, let us begin with the recitation of Dua that will be led by Mr. Muhammad Faiz bin Muhammad Badran.
Bismillahirrahmanirrahim. Al-Fatiha. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma innaka khalaqul azim, innaka sami'un alim, innaka ghafurur rahim, innaka rabbul arsyil azim. Ya Allah, Engkaulah yang mempunyai segala kepujian. Engkaulah yang berhak menerima segala kepujian. Engkaulah yang berhak menerima segala kesyukuran. Engkaulah yang memiliki segala pemerintahan. Di tangan Engkaulah segala kebajikan. Kepada Engkaulah kembali segala urusan. Allahu ya Karim, ya Rahim. Limpahkanlah rahmat dan rahimmu ke atas program Smart Farming International Webinar sesi tahun 2020 yang diadakan pada hari ini. Berkatilah program ini dari awal hingga akhir. Ya Zal Jalali wal Ikram. Kami juga memohon perlindungan darimu dari segala perkara yang boleh mencacat celakan majlis kami, daripada segala perkara yang melalaikan kami, dari berbuat taat kepadamu, kepadamu juga kami serah segala urusan kami. Rabbana alaika tawakkalna wa ilaika anabna wa ilaikal masir. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wa sallam. Walhamdulillahirabbil alamin.
Thank you to Mr. Amir Faiz bin Muhammad Badran for the recitation of Dua. Without further ado, we are now ready to start our talk today. Moving right along, it is now my pleasure to pass to our moderator, Dr. Wan Nozanaria binti Zainal Abdullah, to start our webinar. Please join me to welcome Dr. Wan.
Hi, happy morning to everyone. Happy Saturday and salam, we love UPM. Can you hear me loud and clear?
Yeah,
Hi, Dr. Niza. Hi, Dr. Angelica. Nice to see your smile. Okay, hope everyone is doing well, especially during this pandemic COVID-19. Anyhow, I am very grateful to see abundance of registration and participation to Smart Farming International Webinar 2020, with the total number of registration as 788 registration by 9 p.m. last night. It was a very great number. Amazing registration. You are our wonderful participants from all over the world. For your information, this program is organized by the Malaysian Society of Agricultural and Food Engineers, Student Chapter of UPM Bintulu, MSAE-SC UPM Bintulu. A big round of applause to MSESC and Bintulu Secretariat for organizing this such international event. So as I am a moderator for today's program, so I would like to give a short description about this program and about the smart farming itself. So for your information, smart farming, what I could say is relate with the agriculture industry by applying the right input at the right place, at the right time, with the right amount. What I mean by right input is, for example, the right seed, the right pesticide, herbicide, or water supply. So meaning we apply the right input at the right place with the right amount at the right time in order for us to maximize the production and less the resources. At the same time, we take care of our environment with less waste reduction. So as I am the moderator for today's discussion, not a speaker, we have 3 international speakers. First, from Malaysia, UPM Sedang professor. And the second one is from Australia, Dr. Angelica Suarez. And the third one is Professor Usman Ahmad from Indonesia. Without taking so much time, I would like to invite our first speaker, Dr. Siti Khairuniza Bejo from UPM Sedang. Okay, before I invite her, I would like to introduce a bit of her bibliography. Dr. Siti Khairuniza Bejo is an associate professor at the Department of Biological and Agriculture Engineering, Faculty of Engineering, UPM Sedang, and formerly as a head of department for 3 years duration. Currently, Dr. Niza is the head of Smart Farming Center at Faculty of Engineering, UPM. Furthermore, she also served a research associate at the Institute of Plantation Study, UPM. Dr. Niza obtained her Bachelor of Engineering degree in Computer System and Communication Engineering from UPM and did her PhD degree in Image Processing from the University of Surrey, UK. Her field of specializations are in imaging technology, precision agriculture, remote sensing, and artificial intelligence. She has more than 100 scientific publications, 1 patent, and 4 copyright. What an amazing number and contribution. She also has won gold medal at the International Trade Fair, Ideas, Invention, New Product, AINA, Germany in year 2009. She is the editorial board member of Journal of Information Processing in Agriculture and Journal of Advance in Agriculture, Horticulture, and Entomology. In addition, she is also a professional member of Malaysian Society of Agriculture and Food Engineers, MSAE, a member of Malaysian Remote Sensing Society and the Institutions of Engineering, Technology, and the National Society of Precision Agriculture, ISPA. What an amazing achievement. Okay, just a short sharing for today's information. Okay, this week marks of our 3 years experience together in precision farming study tour in New Zealand in year 2017 for about 10 days. What a great experience we had. We had a lot of learning curve by exploring numerous smart farming industry there. I suddenly missed beautiful scenery of New Zealand. It was so great experience. So, before I inviting our first and foremost distinguished speaker to start the session, I want to reflect something about Dr. Niza Bejo. 3 words that I could say about her are, start with 3P, 3 Ps. Passionate, proactive, and peace. Peace, no war. Yes, indeed, she is so cool. So, without further ado, I welcome Associate Professor Dr. Siti Khairuniza Bejo to present her topic on Agriculture 4.0, Digital Transformation Driven by the Internet of Things, IoT, and Artificial Intelligence. Dr. Niza, the floor is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning everyone. I hope you can hear my voice. Can you hear me? I just want to check it first. Yes, okay, thank you very much. About the slide, can you see the slide presentation that I shared? Yes. Okay. All right. So that's good. Okay. So first of all, thank you very much for the nice introduction, Dr. Wan. Very nice. And then of course, for today also there is no war, peace, no war. Yeah. So basically, yes. And also, thank you very much to the participant. Because you are spending your early morning in Saturday, okay, to attend this kind of the webinar session, okay. Okay, so maybe I can start with my presentation. Okay, so the title is Agriculture 4.0. So in this presentation, I will share with the in terms of the how the digital transformation driven by the IoT and AI that can be driven to the agriculture 4.0. Okay. All right. So the content of my presentation mostly on the Smart Farming Technology Research Center, and then followed by Agricultural Revolution, IoT, AI, case study, and challenges to adaptation, and finally summary. A quick introduction on the Smart Farming Technology Research Center. Okay, as by the word itself, of course, our vision is to lead the charge in enhancing technological advancements in precision agriculture. Okay, and then this is some of our achievement, which is counted from 2018. So in total, we have university grants around 2 million ringgit. And then for the other grants, around 2.4 million ringgit. And then, which means that one comes from the national grant and also private and also international fund. And then in terms of publication, so we have journal publication 568. And book chapters and also book with 6, patent file 11, and patent granted 2. And then we have international collaboration with USA, Germany, of course, Indonesia, Taiwan, Japan, and also New Zealand. And our core business, more on the research, which is 97%, and services for 3%. We also active to engage with the local company such as Ndvi, NPOB, Altiza, PanOS, and so on. Okay. So we move to our core business today, right? So our core business in terms of the agriculture 4.0. So before that, we see that how the revolution of the agriculture. Okay, it start from the agriculture 4.1. Of course, in that one, it is more on the manpower and animal forces. And then because we only use the simple tools, okay? And then during the 19th century, when it goes to agriculture 2.0, you can see that introduction on the agricultural machinery and also usage of chemicals. And then during the agriculture 3.0, which start on the 20th century, you can see that computer programs used in agriculture and also deployment of the robots. And currently, we are in the agriculture 4.0. What is the difference? The difference in terms of the smart systems and also smart devices. It is because of the development of the Internet of Things, blockchain, AI, and also cloud computing. Actually, a lot of things, which means including a lot of technologies. So the agriculture 4.0 implies a transformation of the production infrastructure with respect to connected farms, connected tractors, and new agricultural equipment. So some background, this one is in terms of the how agriculture 4.0 in terms of the connected farm. So you can see that the ideal condition of the agriculture 4.0, we will have drones to survey the field, mapping the weeds, yield, and soil variation. So it will enable precise application of input, mapping, and also to see the condition of the plantation in the whole or large scale. And then at the ground, we will have the agripods. What it will do? It will do the for the crops monitoring and also weeding and also fertilizing, okay, and also harvesting. It can reduce fertilizer cost by 99.9%. At the same time, we will have the smart tractor. The smart tractor is actually controlled by GPS, okay? So meaning to say that this tractor can go a correct direction. So then we can reduce the cost of the fuel by 10%. And in the dairy farm, we can have the texting cows, where it have the, for example, RFID, in order to monitor the condition, the healthiness, or maybe the production of the cow itself. And then you can imagine that all of the data will be transferred into cloud. For what? For analysis. Analysis is used for the decision. And then meaning to say that the farmer don't have to go to the farm. They just stay at home, as what we did now, okay? And then monitor the farm remotely, all right? So that is the ideal condition of the agriculture 4.0. And I believe that the whole world is going towards that direction. So based on the machine research, it has been found that they expect that 225 million of the connected devices will be used in agriculture in the year of 2024. Okay. So this is for Malaysia. National policy of the IR 4.0. It comes in 2018 to position Malaysia as total solution provider for the manufacturing sector in the Asia Pacific by 2025. So you can see that these are the technologies that driven to the digital transformation, which means I highlight that it includes the artificial intelligence and also IoT, which is the topics that I will discuss today. So what is IoT? Actually, I believe that all of you know at least the application of IoT itself. But for today, let's make it clear what are the components of IoT, so then you can use this fundamental to develop your own IoT system. So actually the IoT refers to a system, interrelated, interconnected objects that are able to collect and transfer data over a wireless network, okay? And then you can see that because of that, you have the component of the things or devices, okay, which is sensor, with sensor, and then you will have the gateway, and then you will have cloud, and then analytic and user interface. And then according to FOA, the IoT has potential to have increased agricultural productivity by 70% by 2050. Okay, that is the powerful of IoT. So we go to the component itself. So you have the smart devices and sensor device connectivity. So this sensor will continuously collect data from the environment and transmit the information to the next layer. So currently there's a lot of sensors available. Okay, so for example, this is the Altiza Smart Agriculture Kit. They have the soil EC and moisture, pH, temperature, solar panel, and others, meaning to say that we can add as long as you know where is the sensor that you want. So for this one, sensor platform, there's a lot of platform. It can be from space, from skies, or from the ground. So how the devices are connected? Okay, it's the same as, for example, for us, we need internet, right? So for this one, most modern smart devices can be connected to satellite connectivity or GPRS, or for example, LoRaWAN. So you can see this is the class of the connection. For example, for the short range, less than 10 meters, local area, less than 100 meters, and wide area, which is outdoor, is around kilometers or miles. So for example, for smart agriculture, we'll use this outdoor. And then you will familiar with, for example, the GSM that we use, and then also GPRS for data internet, okay? And also, for example, the LoRaWAN, okay? So after the sensors, we need the gateway. What is the purpose of gateway? It's actually the bridge between the sensor and the cloud. So it can communicate with sensor or devices over varying connectivity types and then translate the data into a standard protocol and then send to the cloud. And then currently there are two types of the gateway. The first one is without smart device sensor, and the other one is smart device sensor, meaning to say that there is a device with the sensor together, okay? And then the cloud. So the cloud will collect, process, and manage, and also store huge amount of data in real time. So you can imagine that. I mean, from my previous slide, from my first slide of the introduction, you can see that we can have data from the drone, maybe from the tractor, maybe from the agri-bot, maybe from the dairy farm. So, what is that? Shared content. So for this one, you can see that lots of data. Okay, so currently, most of the system just collect the data. They did not filter the data. So meaning to say that you can imagine that there is some kind of jam, traffic jam at the cloud. So the current technologies allow us, for example, to reduce the data, just transfer the data, only the important one, to the cloud. This is done at the gateway. After getting the data, we need to analyze. This is data analytics. Normally, we use the AI. So what is AI? AI is the development of computer system that are capable of performing tasks that require human intelligence, such as decision making, object detection, solving complex problems, and so on. Okay, so it is very intelligent. And this is the stages of AI. So we are now actually at the up to stage number 2, whereas the stage number 1 is on the machine learning, and stage number 2 is more on the machine intelligence. And then we can see here, I mean, in this slide, I will share with you about both of the stages. So according to market and markets, it will be estimated 1 billion USD in 2020 for the AI market, and projected to reach USD 4 billion by 2026. Okay, I share here because I know that you are the one who will face this condition, because we are depending on you in order to digitize our agriculture. So at least you know that what are the market in the future for the IOI and also for the AI. Okay, so it is promising. Why? Because due to the increasing implementation of data generation through sensors and aerial images of crops, increasing crop productivity through deep learning, and government support for the adoption of modern agriculture technique. And then finally, the user interface. So user interface is only the kind of GUI. So for example, you can see that how they put for the temperature, we can read the humidity and so on. Okay, so that is the whole concept of the IoT system. Now, I will share with you the case study that myself and my research team work on the plant monitoring system for disease management by using IoT. So it is more on the disease, okay? So basically, to be specific, it is the Ganoderma boninens, okay? The oil palm. It is happened, for example, in Malaysia and also in Indonesia. So technology use IoT, sensor, and artificial intelligence. Okay, on your left is actually the structure. And then I just highlight in terms of the parameter use. For example, we measure the soil moisture, soil EC, soil temperature. It is collected by the MAC10 sensor. And then we also measure the environmental temperature and humidity to see that, because it is like, this one is research. I mean, we are not, there is no available device in the market. So it is research we want to develop. So meaning to say that we want to study that, is there any effect on that? So we use connection of the 3G and gateway of Espresso Lite V2. And we use the ThinkSpeak at the cloud and analysis by using MATLAB toolbox for the machine learning. Okay. So if you go to http myganoonline.com, you will see this interface. Okay. It is actually, if you type, you can go there, okay? But of course, I mean, you cannot enter. Please don't try to enter lah, okay? Because this is our system. So then, basically the user can see the data in the web application. I mean, instead of, for example, they put the dashboard, for example, in all of those things, we put the website, okay? So meaning to say that, for example, the user can see, for example, the condition of the soil, the condition of the moisture content of the soil, temperature, and so on. And then if the data or if the value exceed a certain value, a certain number, it will indicate or it will give alarming system through Twitter, okay? So it will mention to the user then, okay, the value is exceed the level. And then based on our analysis, we use all soil parameter. It is performed better in order to detect the Ganoderma condition. I didn't share the detail because actually my student is now still writing a thesis and in the process of writing a paper. So I cannot share all, okay? Maybe later if it is published, then I can share, okay? So the system can detect Gano at the seedling stage with the age of 5 months as early as 3 months after infection with 98% accuracy, which is very good, okay? Because we can use this for the company to try to produce, for example, a good breed, and then, for example, to produce the fertilizer, or I mean not fertilizer, for example, the herbicide, okay, to kill the things, and then to use this information. Okay, actually the same thing also happened being applied in Indonesia from the Smart Cocoa Research Station in Indonesia. So you can see that it is also for the disease detection, and then it put also that the aim is to provide disease-resistant clones and to encourage farmers to take care of the environment and deter pests. You can see that the system, they got a sensor. Basically, the sensor measure temperature, humidity, PAR, soil water potential, and soil AC, okay? And then they transfer the data using 3G to the cloud, okay? And then, of course, because this is a rural area, they got some problems, for example, to transfer the data. So they also put a server over there, meaning to say that when the connection is okay, then it will transfer to the cloud. So you can see that actually the process is the same. Other one is that for the greenhouse farming in Cambron, Highland, Malaysia, okay. So for this one is actually in order to monitor the condition of the plant itself, vegetables itself. And then they developed by using LoRa-1, okay, to monitor, because LoRa-1 can cover 18 to 20 kilometers, okay, area. And then the sensor also is type of the LoRa-enabled sensor. And then, of course, basically they will monitor soil moisture, EC, pH, temperature, humidity, and weather. You can see here that actually the trend is almost the same, but the thing is that how can you use that? And then in terms of your data analytics is very important in order to make a prediction. Of course, it can reduce, they found that it can reduce the labor 8 hours, okay, per day. And then reduction amount of fertilizer by up to 30%. And increase paper yield up to 20 to 30%. Other things also in the open farm. Okay, this is the smart mitigation system for Chile, also developed by the Altiza. Okay, this one is actually commercialized. So of course they will use the data of the soil condition, humidity, and then if you can see, I don't know, I should have a pointer here. Yeah. Okay, so you can see here that this is the mitigation skid, okay? And then this is the system here. They will have the EC meter and also all sort of pump, sensor hub, and then switch and so on meter pump, okay? So what happens is that they will monitor the tank, okay? They will monitor the tank, and then based on that, they will read the EC value, and then based on that, they also put a sensor, but not all of the Chile plant, but on this specific location. And then based on that reading, they will do some kind of the action. Okay, so this one could reduce cost of fertilizer by 10 to 50%. And for this one, the new one, I can say the new one, because before this, I mean, I went to that chili farm before, but this one I found out that is quite new. If not mistaken, this year. This is for pineapple farm monitoring. Okay, but this one there is kind of the advancements in terms of that they put some kind of the tractor tracking. Okay, tractor tracking, and also additional of the pest control and also the drones. That is the new element that has been implemented in this company, SAT Asia. Okay, so it's hang. Okay, so all of those things before, this is the examples of the open farm. Okay, so we now go to the examples of the closed farm or closed environment. Why the closed environment is important? Okay, it should be much easier because you can control the pest and disease. Okay, because it's all controlled. So the aim is in order to get the high yield as compared to the open farm. You need to control the pest and disease. Okay. Okay, so for example, they put the CO2, okay, because the plant needs twice the level of CO2 than what the in the atmosphere, and then at the same time they control the humidity and also the in order to avoid the fungicide and also bacteria, and then you can see that here this is the spectrum, okay. The spectrum here is that in order to see that what are kind of the light that is important that gives some significant contribution to the growth of the plant. Okay, so as if I'm mistaken, normally is blue, but of course currently researcher is still doing this research in terms of to get the best spectrum for the growth of the plant, and then they use the hydroponic. Hydroponic meaning to say that it will receive a constant circulation of natural nutrients, okay? And then this closed loop cycle allows the roots to easily absorb the necessary water and nutrient. But you can see that normally it will be implemented in the high value crops because yes, it is very huge investment. So because of that, if it is like high value crop, so you will get a good return, okay? But you can see that because of that, you can reduce the space to plant the vegetables. So for this one, you see, it can reduce water, energy, space, capital, and also labor. And then water by 90%. And at the same time, vertical farming can grow as much food as 0.7 acre of traditional farmland. Okay, of course, because it's stacking. You can imagine that you are parking your car in your shopping mall. Okay. Okay, this is just an example. Okay, I mean, City Farm has developed a lot of type of vertical farming and also closed farm. Okay, so then meaning to say that people can just use it. Okay, now I go to the artificial intelligence for the stage number 1, meaning to say that for the machine learning. Because you can imagine that artificial intelligence is part of the IoT, but at the same time, it can work alone because it is like, I mean, it can be only AI, also part of the Agri 4.0 because it stands to the digitalization, okay? So for this one, you can see some of the process, for example, to develop the machine learning, okay? Stage 1 is machine learning, yeah? So the first one, get data, and then clean, prepare, or manipulate data. But in the right way is that, for example, feature extraction. What are the properties that you want to use? And then you train the model, and then you test the data, and then you can get the improved model. So because unfortunately my work is more on the disease detection, so I just give you examples of the disease detection. But of course, I mean, as what I said, the concept is the same. I mean, you can change to the application that you want to use. So for example, it's for soil-borne disease. You can see that this is at the nursery and also at the plantation level. So this one, the very difficult part is things that, I mean, seed of tree that is like, there is no symptom, okay? It's similar with the, for example, our COVID-19. If it's no symptom, how do you know that it is like infection, right? So it's the same, okay? No symptom, low symptom, and so on. But this one is quite easy because, yeah, it tends to die actually. Okay, and also for the mature tree, mature palm, okay? So basically for the mature plum, these are the things that being taken into consideration in order to detect based on the human, for example, human vision, in terms of the filial symptoms, in terms of also the fruity bodies, and also the crown condition. So now, as what I said, the first one is in order to check the properties that is important that can give indicator on the existing of that disease, for example. Okay, so this one we analyze the changes of all palm canopy architecture by using a terrestrial laser scanner. So for this one, we check for the crown area and also front features. Okay, so you can see that we found that all of these will significant with the condition of the disease. So you can see here that this is the graph of the crown pixel. It will be decreased. The number or the crown of the area of the crown will decrease when the severity level is increased from healthy, mild, moderate, and severe infection. It is same goes to the front number. So basically this is the front number. Meaning to say that it is like severe, it is less front. And then we also see that there is a trend for the degree between front. So this is the degree between front. So when it is severe, of course, due to the less front number, so the degree of between front is higher. That is the finding of this paper. And then we go further in order to check the stratification, okay, this one. So meaning to say that based on the data, based on the point cloud data that we have per tree, we try to slice, okay, we try to slice until 17 slices, okay. And then based on this slice, we try to analyze, okay. For example, this is the crown profile of the healthy and non-healthy. So from this crown profile, it is shown that the healthy part is more dense as compared to the unhealthy part. Okay, it starts from the 250 until 890. And then you will have the accuracy of 92.5% and kappa coefficient of 0.83%. Okay. So we go further for the by using significant parameters. For example, just selecting strata number 200 and also 850, and also crown pixel and front number and front angle. So from here, we found at the combination of the front number, front angle, and also S200, okay, the level of 200 will give us high percentage of accuracy in terms of the different level of detection and also healthy and non-healthy. I know because the time is that another 7 minutes, okay? So this one, then later we do the machine learning. Okay, so it comes to machine learning when we really confirm what are the elements that we want to use as our features. All right. So based on this, we introduce the PCA. We do it the PCA, and then we found out that the contribution of the PCA is more on the PCA1 and PCA2. Where PCA1 and PCA2 give us information about the front number, front angle, and crown area. This is the content of the PC1. And for the PC2 is more on the strata 200 and 850. And then we create our model by using a different combination, and the best combination we test with the different sample, okay? So it found that we can get the multiple level accuracy, meaning to say that at that 4 severity levels of 85%. Each means that it gives better percentage as compared to the previous one, okay? I mean the previous one is linear model as I described before. Okay, so we also use the thermal imaging. For the thermal imaging, you can see that there's some different. Okay, thermal imaging also quite famous because in airport nowadays, in order to check COVID or not, they put thermal, right? So thermal camera. So this one also almost the same. So for example, when it is healthy, it is more cold as compared to unhealthy. So for this one, we found that by using SVM, it can give us 89.2%, but this one is during the development of the model. And when we test, it is 84%. However, it is only healthy and non-healthy condition, not the severity level. So other than that, we also use the hyperspectral imaging. This one is for the seedling, okay, seedling. And then we found that this is the most band that can be used. And then we try to reduce the number of bands from 35 to 5. And then we found that linear SVM, Gaussian SVM, and also medium Gaussian SVM give a good result, okay, because it's just 1% less as compared to, for example, 18 number of input. So that one, so we also have the, as what I said, the stage 2 of the artificial intelligence is deep learning, okay. So the difference of deep learning is you don't have to extract the features, okay. So you don't have to extract the features, you just run, okay. So this is some of the example, very quick example. So this one is to detect the pest, okay, the pest attack. So you can see that the healthy flies attack and spider attacks, it is in capsicum actually. So you can see that there is like can detect 100% of healthy and as compared to the attack itself, okay. So other than that, you can see a lot of application, okay. As what I said, it's not only in the disease, but for example, for planting, weeding, plant counting, nitrogen, irrigation, harvesting, and so on. And also currently spraying, it is very good or very intelligent because the spray can adjust the amount of spray, amount of fertilizer, for example. Even for example, you change the speed. Even for example, different terrain elevation, it can try to adjust, okay? So the challenges, of course, the first one is farm machine need to talk each other. It is similar as human, okay? We have one language so that we can talk to each other, okay? So the machine also the same. And then of course, in terms of the infrastructure, because over 4 billion people around the world live in unconnected rural area. So we have to provide a good infrastructure. And then aging farmer, huge investment, and also needed training. So this is the summary. So IoT, what is that? Is anything connected to the internet. So the structure is sensor with gateway plus cloud. And then it can be indoor farm. Of course, indoor is controlled environment. So the focus basically is in order to get good recipe of the vegetables. And then outdoor, you can have the pest and disease, okay? And then LoRaWAN can solve issue of connectivity. And then drone can be used. Can be used to tour the sky. To cover the whole area, the big area. And then the robot, okay? The robot can go to do some action, and then at the same time to provide the monitoring or detection. Of course, the head, the intelligence system, goes to AI to do some decision. Of course, the advantage is to get higher yield, better crop, less labor, remote monitoring, reduce crop loss, reduce the usage of fertilizer and pesticide. So at the same time, I would like to invite all of you to join our next year's conference, KVI 2020. Okay, next year, but 2020, because actually it should happen this year, but due to COVID, we postpone to next year. It is online, so it doesn't matter. You don't have to spend your money for the hotel, for the flight ticket. Okay, it is online. And it just costs you 100 ringgit for the keynote session. But if you join the whole session, 2 days, it will be 150 ringgit only. So please register before 21st December 2020. You have ample time, okay, to for example, to collect money, okay. So with that, thank you. I try to finish at 9.
Yeah, thank you very much, Dr. Niza. You are sharp on time. That's what I say. You are very cool. Cool, yeah?
Okay, cool. Okay, thank you.
Okay, thank you very much, Associate Professor Dr. Niza Khairuniza Bejo, on her presentation on the topic of Agriculture 4.0, digital transformation driven by the Internet of Things and artificial intelligence. A big round of applause to Dr. Niza. Wonderful, wonderful, wonderful session just now. What I can conclude is world now is progressing well in the field of smart farming or precision agriculture with the great advancements of technologies. Do you agree with me? I'm sure, because as you can see from the presentation just now, so the advancements in technology makes our agriculture industry work very well and progressive well now. So is there any question from the floor to Dr. Niza on her topic? Kindly grab this wonderful chance to ask her. So as I can see from the chat session, here we got one question. Can you hear my voice well? Hello?
Yes.
Yes, okay. I got one question from Mr. Azmi bin Akmal. How can Malaysia, especially in the West Malaysia area, can apply the IoT and artificial intelligence technology in agriculture industry if our zone have unstable internet connection?
Okay, yeah. Okay, so because of that, there is a technology of the LoRaWAN that can be used for the rural area, because they will try to provide, for example, some kind of the tower to connect, okay? And then the most important part is you need to know what are the elements that you want to transfer. So basically, in agriculture, the data is very small, okay? Just value. I mean, you not really tends to use, for example, images. And then as what I said, currently, for example, most of the people just transfer their data to cloud. Okay, that means that as what I said before, it will be traffic jam in cloud. But currently, you can process the data in your, gateway. Meaning to say that from the location to the, on the ground. On the ground, for example, you collect LoRaWAN, okay, you transfer the data from the ground, you try to process. And then only important things you will transfer to the cloud. So then you can reduce the data, the amount of data to be transferred. Okay? How is okay?
Okay, thank you for the wonderful answer just now, Dr. Niza. So we got another one question from Sasi Kumar. So in Malaysia, approximately when we can fully using full force of AI and IoT in our agriculture industry?
You said when?
Yes, when we can fully utilize full force of AI and IoT in our agriculture industry.
Okay, yeah. I think I'm not the one to answer because okay, but I can share with you. Because of that, in terms of to make sure that the technology works smoothly, it is not only, for example, to be depending on the researcher, but it is like support from all parties. For example, from the government, it's the same goes to the, for example, connection and so on, yeah. So from the government, from the company, for example, but you can see nowadays, there's a lot of company goes into that direction. For example, as what I said, the LTZ, that company provide, as what I know, to the IoT systems, to the for aquaculture and also for plantation, farm, okay? So meaning to say that we cannot say that I don't have any idea when it is fully, but of course the government also put all of support. Because you can see based on that IR 4.0, that direction as stated with you, that is 2018. Meaning to say that even, for example, in the Department of Agriculture, department of the, or MARDI, for example, they also try to make a direction towards the use of the agriculture 4.0. So it is very promising for that, but the exact time is, I guess it is from time to time. Okay.
Dengar tak? Okay, what I could add on the Dr. Niza answer just now. Yes, we are slowly but surely. So we are slowly progressing towards the applications of artificial intelligence and IoT in our agriculture industry, but slowly and surely. Okay, thank you very much for that. Okay, our final question from Muhammad Hashrin Hassan. I think this is my student who joined my class, Precision Agriculture Technology from BSBI, Bioindustry class. IoT and artificial intelligence usually used in pest management, in monitoring and detecting visible or above soil surface sign and symptom of pest outbreak or infection. How about the one which affect the plant under the soil surface, which does not show any or less symptom on the plant, such as nematode?
Okay. So under the soil surface, isn't it?
Yes, exactly.
Okay, yeah. So basically, that Ganoderma is in fact to the soil, basically, under the soil surface. And then we put the sensor inside. I mean, under the soil. If not, it's not. Because it comes from that. Okay, normally it's that. I mean, fungicide and also pathogen. That one is the, as what I share with you, is the soil-borne. So meaning to say that, as what I did, I tried to monitor the EC and also the temperature and also the moisture, because as you see that one is things that is related. So meaning to say that if you want to monitor some of the things, I mean, due to that, you said that nematode whatsoever, you have to check that what are the things that can give some influence to that disease can happen. Okay, and then of course, after that fundamental study has been made, then you can check the available sensors that can be used. But at the same time, it's also important to monitor the weather or environment condition, because it also affects the situation of the disease occurrence. Okay, that is my answer.
Okay, thank you very much, Associate Professor Dr. Siti Khairuniza Bejo, and thank you everyone, especially to those who throw your questions just now. It was a wonderful station, Q&A, and two-way communication among us. Once again, thank you very much, Dr. Niza. Okay, our first speaker is done, and we are now, can't wait to hear from the second distinguished speaker for Smart Farming International Webinar 2020, which is Dr. Angelica Luz Suarez from University of New England, Australia. For your information, Dr. Angelica and I used to be in the research group while we are pursuing our PhD degree in University of Southern Queensland, USQ, Australia before. And we also used to stay at the same research center at Australian Centre for Sustainable Catchment, ACAC, USQ in year 2012 until 2015. And we also had an experience, I also had an experience following Dr. Angelica for her data collection session at the Darling Down Cotton Farm. So it was wonderful memories at that time. So before I invite Dr. Angelica, so I would like to express her short bibliography. So Dr. Luz Angelica Suarez, her full name, is a research fellow with the Applied Agriculture Remote Sensing Center, AARSC, at University of New England, Australia. She has been involved in spatial science and agricultural research since 2005 in diverse industries, such as for coffee, cotton, grain, and vegetable. Her research interest is more on developing methodologies that facilitate and increase better management practice by, first, the proper evaluation and adoption of remote sensing technologies. The second one is analysis of environmental variable and crop production factor in yield performance. And the third one is crop variability and health assessment. Fourth, mapping and generations of spatial data. And last but not least, for yield forecasting. Her expertise include hemispherical, LiDAR, hyperspectral and multispectral sensors in proximal and remote sensing platform applied to land administration and agriculture and a broad range of sophisticated statistical approach. What a wonderful experience. Well done, Dr. Angelica. Dr. Angelica did her bachelor and honors in topographic engineering, land surveying in Colombia, and started her career working on coffee at the International Center for Tropical Agriculture in Cali, Colombia. She did her master's degree at the Jain University in Spain, focusing on developing semi-automatic methodologies for detections of new infrastructure to support land administration decision and cadastral survey data updated. In addition to that, she did her PhD degree in Australia remote sensing with the University of Southern Queensland, Toowoomba, Australia, with me at that time. I witnessed her great effort in doing her PhD. He did a very good job. Her thesis, founded by the Cotton Research and Development Corporation, CRDC, assesses proximal and remote sensing technology for predicting yield loss as a result of herbicide drift. So Dr. Angelica is leading the establishment of international relationship with highly ranked research institutions and industries in Latin America due to her understanding of the present needs and challenge of the agricultural system in this region. So her research interest is focusing more on the agriculture system, time series analysis, remote sensing, and statistics. She has a lot of publication right now and with a very good H index. Without further ado, I would like, in addition to that, so the three words that I can reflect Dr. Angelica, you guess what kind of alphabet that I want to use today for her. Dr. Niza, just now I choose 3 P's, and for Dr. Angelica, I use 3A. She is very outstanding, awesome, and active. Without further ado, I would like to welcome our second distinguished speaker, Dr. Angelica Suarez, to present her topic on his perspective in handling smart farming. Welcome. The floor is yours, Dr. Angelica.
Well, thank you very much. I hope you can hear me properly.
Yes, loud and clear.
That was a magnificent introduction. Thank you very much. I'm very, very honored to be here. Thank you, honestly, for this invitation. It's the very first time that I'm talking to this sort of audience, so I really appreciate that. So let's start. So yes, my talk today is the remote sensing application for precision agriculture. I'm going to give an idea of where we are, who we are, and what we're trying to do. So representing the Applied Agricultural Remote Sensing Center based in Armidale, a small town in Australia, and associated to the University of New England. We have, this is the current footprint of the most recent research projects. And as you can see here, we are basically all over the agricultural land in Australia, covering many different industries. We focus on industry needs. We know this technology, and for all of you, this is a tool that is not going to give you the full answer, okay? You need to bring all these different technologies that the first speaker was talking, and then what I'm going to talk about, and many others. The idea is to combine them so you can have a better decision in your farm. So before we start, remote sensing is just the acquisition of information of an object or phenomena without making physical contact. So we don't need to touch the crop. We don't need to touch the surface of the object just to know what it is about. And the principles of this, I want to cover this because I'm not sure how familiar you are with this, but the healthy canopy reflects a lot of energy in the near infrared, which is a band, and very few energy in the visible bands that are like the blue, red, and green bands. The unhealthy canopy does the opposite. So that allows us to differentiate between the crop condition. If we put this in an Ndvi example, Ndvi is a very famous vegetation index that is currently used across many agricultural applications. So the healthy vegetation will reflect more, will give us a higher index value, and the unhealthy vegetation is doing the opposite. So just keep in mind, Ndvi is a really good indication or indicator of vigor, but there are many other different indices, more than 100, that can be better correlated with the parameter that you are interested in. That one could be yield, could be pest disease, could be water management, could be anything. Just keep that in mind. So in remote sensing, we talk about proximal and remote platforms. As a remote platform, we have satellites, aerial, UAVs, or drones. And then as a proximal platform, we have lifting or ground-based because they are closer to the object. We talk about resolutions, it's very important, and the purpose will dictate what sort of resolution you need to use. So during my talk, I'm going to cover different applications and the different resolutions. In general, we talk about the spatial, is the pixel size, how much detail you're gonna get from an imagery. Usually, the bigger the pixel, the bigger the area, okay, but less the detail. The temporal is talking about the frequency of image acquisition for some purposes like water management. You need daily, ideally daily or very or highly frequent imagery captures. But for some other applications, once every 2 weeks or once every 6 months or once a year, depending, it's good enough. So the temporal resolution. The spectral is talking about the number and width of wavelengths. So here we have the multispectral sensors and hyperspectral sensors. Again, the purpose will dictate what sort of sensors you need to choose. And radiometric is more on the data sensitivity. So satellites, we have lots of satellites available right now, covering the entire globe every day. We have different missions in different regions, and we just need to pick the one that better suits our needs. And in terms of drones, again, we have many as well. Recently, there are huge advances in this area. The benefits of those is that it can be deployed at short time, relatively low-cost platform in comparison with a satellite, for example. It can provide overhead imagery of agricultural crops in varying forms like RGBs, near-infrared, thermal, or LiDAR. And because of that, you can develop optical height models. Now, the limitations is that they are generally uncalibrated. They have a limited flight time, line of sight restrictions privacy issues. I don't know there, but here people is not very comfortable knowing that they have a drone flying over their houses or over their farms. So it requires certification to operate commercially. It requires ongoing maintenance and repair costs, and the data processing and interpretation it's time consuming. Okay, so just this, I wanted to, sorry, I got distracted. The optimal, this is a PhD student. He was assessing the different configurations or just to identify the optimal settings of flying a drone for horticulture. And so he tests the drone and camera systems, the mission planning, the ground control maker, and the reflection targets. And from here, the student has 28 different configurations where it has the above ground altitude, tests different ones, image size, overlap as well, different percentage, the flight speed, the flight time, because depending on the sun angle, the sun elevation is going to give you more or less shadow, and that is extremely important for, particularly for tree crops, and then the flight pattern. So from here, it was like a conclusion, or quite a few conclusions, is that the recommended image side lab is around 75%. That you need to have calibration panels for radiometric and geometric correction, and this is something that often commercial companies are not doing. And for agricultural purposes, this is extremely important. So the flying with high forward overlap improves the accuracy. The higher image resolutions improves the accuracy as well. Flying at a high solar elevation, again, because you have less shadows produced by the sun. Anyway, many different ones. The reference out there if you want to go through those. So UAV cameras, we have many, all of them. They have different settings, different bandwidths. And what is that telling us is that if you fly, just keep that in mind, if you fly your trials or your farm with a camera system, and you develop an algorithm to predict, in this case, nitrogen uptake, you have to be consistent on the camera system you're gonna use. You cannot just swap the system and then trying to use the same fit to predict nitrogen uptake, because it doesn't work like that, okay? So here are the differences. It is possible to do it, but the fit and the regression analysis is completely different. And that is because the configuration of this camera system is different. All right, and choosing the right vegetation index is something to consider as well. And this one doesn't apply just to drones, but to everything. Examples again in rice, very often we use Ndvi for this sort of applications. But what happens is that Ndvi saturates. When I say saturate, is that here we're seeing a nitrogen uptake from 50 to 200 kilograms per hectare. Here, from 50 to 200, but the index is not showing any variability at all. So if you base your prescription maps on this index, then you're gonna cause reduced yield potential or reduced cold tolerance. Now you need to really pick the right index, an index that is not saturated, okay? And the resolution. We often hear about that 2 centimeters or very tiny pixel size is the best to go. again, it depends on the purpose. So here we can see very clearly the tree crown delineation of these crops. But what happened is that you can lose the spatial integrity at the orchard level. So if the grower wants to manage the growth, that is what I'm gonna have. That's what is going to have. Like a lot of noise. It's really hard to decide how to target or how to improve whatever areas the grower needs to improve in the field. So in that cases, it's better to reduce the spatial resolution to get zones. So now the grower can actually manage the growth, we call growth or block, per zone. Again, the purpose dictates what sort of resolution you need to use. In comparison, coming back to satellite platforms, we have Borne 3 is and very soon Pleiades is another one with the highest spatial resolution, but it has a cost associated to that imagery. Now, if we move to Sentinel, Sentinel has a higher frequency, it's every 5 days. It's a free access satellite imagery, but it provides 10 meters resolution. In many cases, that's more than enough. But in some others, it's not really the best one. So again, the purpose. Now we have Planet. It has a higher revisit time between 1 to 2 days. There is a cost associated that is not yet very clear, but the frequency is ideal for irrigation purposes, for example. Now, the Landsat is 30 meters, it's every 16 days, but it's the only sensor or the only imagery that we have available from early 90s. So if we need to do time series going back that long, it's the only sensor that we could use. So again, the purpose. Okay, so how to use remote sensing for precision ag applications. Keep in mind, this is what we're doing. This is an example of the carrot crop. This is how it looks on the ground. This is the canopy. You cannot see the crop. You cannot see the carrot. And this is from the satellite. And what you're trying to do, or what we were trying to do here, is to estimate yield. How much yield in tons per hectare is being produced in that pivot. Something like this. Sorry. This should be. I don't know what's going on. So what we're trying to estimate is how much of those carrots, estimate the amounts of carrots that are being harvested using the satellite. And for that, we need to go to the field and collect the samples so we can actually transform the pixel value into tons per hectare to get an equation like this. That's what we do. The approach is very simple. The satellite capture, then we process for fieldwork, and I'm going to explain what I mean by that. The data collection, the image analysis, and then the product. In my case of this talk, usually we're talking about yield maps is our main product. So for fieldwork, what happened is that we need to, when we're using satellites or any sort of remote sensing platform, we want to get the variability, we want to capture the variability that is happening in that field. So the only way to do it is you can do it randomly, or you can use Vigor as a guidance of where to go. Now, this example, you can see is very difficult to see any sort of variability. From here, what I can see is a quite homogeneous canopy. But when you put it as a Vigor map, then it's a completely different story. So using this information, you can better decide, okay, I'm going to select my sampling points in this area, some others here, some others here, and then I'm going to increase the likelihood to capture the variability that is happening within that field. If you only capture points along this line, then you won't be accurately predict what's happening in this area here, okay? In tree crops, this is what happened. This is how it looks. Areas of dead trees with dead trees, and in the ground, this is how it looks. Now the medium or the low vigor trees in a vigor map looks like this, but in reality on the ground is here. It's a very poor canopy, lots of interrows, exposure. But when we move to medium, so all of this area within that row or within that block looks like that. And the trees that we found in the field looks like this. So a bit bigger, a bit healthier, but definitely the high vigor trees are completely different. The canopies, they are touching each other. You don't have that much exposure in terms of interrows, etc. And fieldwork, then we georeference the points, the sampling points. This is an example of the carrot fields. We delimit the sampling area, and here we collect samples, and we transform that samples. We put it in in units in terms of times per hectare. If we're talking about tree crops, then we talk about kilograms per tree or tons per hectare, whatever unit the grower is more comfortable with. And we harvest everything for all of those points that we select in the field, and we proceed with grading if that's the purpose of the project. Now, this regression fit now is what we use to translate the reflectance value into tons per hectare or yield or any other parameter, right? So we test more than 20 different indices and see which one is better representing the variability in terms of yield. We design the fits, and then we transform that and we run statistics. And this is an example of the derivative yield maps in olive tree in Arbequina variety. Again, this is not an index value. As you can see here, this is in kilograms per hectare, okay? Using that information, then we can provide this to growers. They can see, okay, this is your yield forecast estimation for a particular block. But more importantly, we can provide yield variability maps, and this one goes to the idea of filling the gap between the maximum potential and the average yield, which is at the very end, the principles of Precision Ag. Increase productivity within the same block. So the grower knows what's happening here are the ideal conditions because these areas here are reaching maximum potential of that block. But this one, so the grower needs to focus on what's going on here and compare. So in that way, if he decide or she decide to intervene the crop, it needs to do it here in order to increase the average yield for that particular block. So be aware when we're using this in tree crops, if you have been working on this, the bearing process of the tree is going to impact the reflectance values and therefore the regression fits that you're going to use. What's happening in trees is that one year they're very healthy, they produce a lot. The following year they are still very healthy, but they don't produce that much because they need to recover, okay? For both years, the canopies are very healthy, and that's why you can see from the satellite or from any drone or remote sensing platform, the canopies are not changing. What is changing is the product, the fruit production. So we need to know how the bearing process is influencing the performance in terms of productivity, and therefore that's how we can better use this sort of technology. That happens for avocados. This is an example of olives, but it happens for all tree crops, say avocados, mangoes, citrus, mandarins, oranges. all the tree crops have the same sort of pattern. And the above ground biomass and yield is also playing something to consider. In crops like carrots, we found that it's not always consistent. So the above ground biomass in these are 3 different regions, main growing regions in Australia. And as you can see here, the relationship between the above ground biomass and yield is not always the same. Okay, that is also going to change the relationship between the reflectance value and the product. Just keep that in mind. I have added some references as well. You can just go through and read the papers if that is of interest for you. Now, the purpose and resolutions, I want to elaborate a little bit more on this. The Worldview 3, as I was mentioning before, it has the highest spatial resolution. It gives you 30 centimeters. It covers a really big, very big areas, and it gives the chances to manage at the tree level. Now, if that's not the purpose, if that's not the need of the grower, then and if the grower wants to do it per zone, now you can try different options. Planet and Sentinel. Sentinel is free. So you are removing the cost associated to the imagery and reducing the cost of the Precision Ag products to the final user. That is very much what we want to do. But again, it depends on the purpose. And in terms of accuracies, for us, it's not just estimations. We need to really be confident that what we're doing is actually accurate, because otherwise we lose the purpose. So as you can see here, Worldview 3, Planet, and Sentinel, they are all within a really good range of accuracies, reaching more than 95% at the block level. This example here is in macadamias. The macadamia industry needed the planting year for all the blocks that they were having in Australia. The only way to do this one was to use Landsat, because as I said before, Landsat is the only one who gives you information back to the 80s. So in this case, we used time series analysis with imagery from 1988 to 2020, because we need to develop this sort of profile per block, okay, to estimate the planting year. So using this sort of approach, we estimate the total macadamia planting area calculated per year for the entire industry in Australia. We also did, we also provide yield forecast models at the block level, and we're doing this using between 3 to 6 months prior harvesting. Why? Because the industry needs this. Once you start working in precision ag, you need to consider the needs of the industry. Otherwise, you lose purpose, okay? Always keep in mind, what is the industry need? The industry need for us needs to be, in this case, was to get a forecasted yield for marketing purposes between 3 to 6 months prior harvest. So that was our main target. We test many different approaches, from individual or the simplistic way of using one single index, or combining several indices plus the climatic variables, all of them. And we found that the best one was using several vegetation indices. That was the best one. It was giving us the ability to estimate yield at the block level, so no variability within the block, but just giving us a value per block in tons per hectare for different regions across Australia. So far, 2020 results for 2 orchards. At the block level, average error is 30%, and the prediction error of total production is 9%, which is again within a really good range of accuracies. This yield forecast is being delivered to growers in web apps. So it's very easy, very easy to engage and to include in the daily activities. Another example is what we're doing with sugar. And sugar, we are providing maps and image products to 98% of the sugar industry. So it means that more than 90,000 crops have been mapped for the entire growing period. What we did is to generate a time series analysis, so we don't rely on a specific capture or time of the capture. We can estimate now very early in the season what is going to be the production per region. What we do is so we have this feed, and now if we get a capture available here, we are using the time series analysis to estimate what is the maximum green Ndvi, because that's what we use in sugarcane. We cannot use Ndvi for the saturation problems that it gets that I explained before. So we estimate the maximum green Ndvi value, and then we estimate the tons per hectare for that region. Again, we're doing this with Landsat, which is available. It doesn't have any charge. We can do it. We don't depend on cloud cover because we have, again, a very big window capture to pick, and then we have this potential to predict early in the growing season, right? And now we are in the process to translate just to move this equation using Landsat to Sentinel, because Sentinel, again, is free and it has a higher revisit time. This is what it looks like. Again, this is not just the index is in tons per hectare, and for this region, you can clearly see what areas are underperforming. And we are giving this to the mills, and the mills are reporting back to the growers saying, look, this is your estimated production. You need to do better. You need to increase. You're doing perfect. So it comes to now the decision management at the farm level. And the national mapping of orchards, this is a different level again, different purpose. And I'm going to play a video after this where we're mapping 6 different commodities of 6 different industries: avocados, bananas, citrus, macadamias, mangoes, and olives. The clusters that you can see here are related to the density of the industry. And if you zoom in the dashboard, and I can send you the link in the chat, it's going to be updated straight away. So if you zoom in that area, you have a reportage of only olive groves of 23 hectares. And this is how it works. Just stay with me. I'm going to play this video.
This is very simple. It's just, it summarizes the area of production for each commodity based on the extent of the map. So moving around the map, you can see these statistics update on the fly, or you can zoom to a specific region in Australia that's preset, and again, the statistics update. We often create applications or use the data for response to natural disasters. We experience many different disasters in Australia, from bushfires to tropical cyclones, and for that we've created the Australian Tree Crop Map Severe Weather app. And this primarily serves as an application to stream in data from the Bureau of Meteorology, including the imagery we're looking at now, which is a almost live capture of the weather over Australia. And we add a bunch of other layers such as the rain radar, but also weather warnings, wind, severe thunderstorms, and of course tropical cyclones. So when a tropical cyclone is active, we'll get a live service with the updated predicted track. The final application I'd like to share with you is around biosecurity. This isn't a specific web application, but in the past we have worked with the biosecurity stakeholders in North Queensland to respond to the TR4 Panama disease, which affects banana plantations in North Queensland. This is really important to know the location and extent of crops, in this example bananas, because it helps set up containment zones, but also to model risk around vectors. This is a soil-borne disease, so knowing where that soil is transported is really critical, and knowing where that soil might come into contact with other banana plantations is how that works. It also helps with response and recovery generally. So that's all I have time for today. If you have
And that is what I was planning to share today. Just to elaborate a little bit more on that and the importance of this information. So again, we are moving from the tree level, so from a very specific applications up to this scale of warning systems. We had a warning of imminent destruction, and then here we had already mapped the location of the crops and which industries were going to be highly affected. So it's extremely important in terms of management, mitigation, prevention and mitigation of natural disasters. Another example, very clear example, is the cyclone Ndvi. We had this situation 2 years ago, more or less, and the red line is the path of the cyclone, and here we have the radius of influence. From here, we could immediately identify the crops that were highly affected or in high risk, and which ones were completely just out of boundary, don't even worry about those. And we could map the area per industry according to the radio. So this is a 50K radio, and this one is 100K radio, and we map the blocks and the area of the individual industries that were affected or were in high risk. This is also important for biosecurity purposes, and in terms of estimations of productivity. This is again an example of the sugarcane region. This region was affected by the cyclone. Here you can see clearly the area that was affected. Before the cyclone, we were saying that there was a regional yield forecast of 90.1 tons per hectare using the algorithm that I showed you before. Now, post-cyclone, as soon as we had an imagery available, and that was around 2 days after the cyclone, we were saying, well, you're not going to get that. You're going to get only 71.2 tons per hectare. And few months later, the actual harvest for that region was 71 tons per hectare. So it is, it works. It is extremely accurate, but it works because we have the data from where we develop all these algorithms. I mentioned before the issues, or not the issues, but the consideration on tree crops in terms of the bearing process, the shifting between seasons and the regression of fits. So you have to really do a estimation per year, but there are other crops that doesn't work like that, are more stable. This is an example of rice, using 4 seasons, multiple varieties and multiple locations to estimate nitrogen uptake using the RIDE index. And you can see here the fit is really good. If we plot the seasonal influence, it's still within the range of the variability that you can expect when you integrate different varieties and different locations. I think this is the last example in terms of mapping and the importance of using train information. And what I mean by that is collecting data in the field if you're going to classify tree crops. Right now, we have lots of different organizations saying, even international organizations say that they can estimate the crop type in Alaska or something like that, you know, crazy places, but they don't provide what is the accuracy of that. They don't really, they only say that they're using artificial intelligence or something like that, but you can use whatever you want as long as you have training data, as long as you have ground validated data that you are 100% sure that what you classify is an actual, for example, vineyard or a cherry crop or a citrus crop and not something else. The only way that you can guarantee that is getting to the field and collecting data. We use the spectral profile of these different of these different crops instead of one single reading. So we use the spectral profile and to classify the crops, and we did it with the industry. So the industry were providing the information to us, and we just developed the algorithms, and we are covering more than 60,000 square kilometers. And the accuracies are very, very good, like higher than 90%. So I guess that's everything I want to share with you today. For you, just keep in mind remote sensing and all the technologies that we talk about in Precision are tools. They are not going to resolve the problems just by using them, okay? It's not one technology competing against another technology. It's not satellites competing against drones or things like that. It's how you use the technology, whatever it is, to address the needs, to respond to the needs, and how you can combine them so you can actually minimize inputs and optimize productivity. That's I think that's my main message. Yeah, and thank you for listening.
Yes, wonderful. Thank you very much, Dr. Angelica, on your presentation on the topic of different application of precision agriculture from my perspective or your own experience. A big round of applause to Dr. Angelica. We are so proud with your achievement. Awesome, dear. Awesome, mate. Yes, indeed. We had witnessed Dr. Angelica expertise through her presentation just now on the aspect of hemispherical, LiDAR, hyperspectral and multispectral sensor in proximal and remote sensing platform for smart farming industry. So you shows us you had applied all this advanced technology for many crops. What a great experience. Wonderful, mate. Me amor.
Thank you.
Okay. Is there any question from the floor to Dr. Angelica on her topic?
I have a question.
Yes, please.
Yes. First and foremost, Dr. Suarez, I'd like to commend you for very good presentation. You captured a whole book in an hour. And but I have this question for you. I'm interested in rice crop plantation, and I'm glad you mentioned it in the early part of your presentation. Two questions in one. The first is that what sensor or camera? I'm interested in the use of drone to capture aerial imagery, and the purpose is to use it also to generate a model for application of pesticide and so on. So what sensor or camera do you think is best suited to capture these images, particularly when we look at cost as well? So that's one. And the second is, you also made mention of the vegetative indexes, which is also suitable. At a point you said that it's not just advisable to use one, like you use maybe through your time series data you've gathered, a combination of some indices were used to generate those prescription maps. So for like the rice crop, what model, what indices do you think is most appropriate? Or which of the combination do you think is most appropriate? Thank you.
Okay, thank you for your question, and I really very pleased to hear that you enjoyed the presentation. There are many things that I didn't cover because of time, but anyway, in terms of which system to use, or drone or camera, again depends on your current situation. What's the purpose of that? If you want to do it, say, covering regions, then I will suggest to start, of course, in your trials, making sure testing different indices. But if you're going to cover regions, you have to go and use a sensor that provides you that whole coverage and is less influenced by topography or growing conditions. In the case that we had here, we used satellite and we used drones. And as I mentioned in the very early slides, it doesn't really matter what sort of system, camera system you're using. They work. You just need to make sure that you have the right information to calibrate your system. Okay. And keep in mind that if you develop something using a particular, say, mica sense, and then you, for different reasons, you cannot use that mica sense anymore, you have to change this to something else, then what you've done is lost, pretty much. Yes. In terms of vegetation indices, which one is better? Yeah, for a rice crop, again, it depends on the purpose. What are you trying to estimate? If you're trying to estimate nitrogen, I will suggest to use the red band.
Sorry?
The red edge band is the band that is highly sensitive to nitrogen and pigments and nutrient concentration. And it works. It is very consistent regardless the crop. So if you use the red edge, that one is usually any index that use that red edge band. It's going to be much better than any other. But again, it's a testing. You really have to test which one is the best one for your case.
Okay, thank you very much.
Yeah, I hope I answer your question.
I'm okay. I will still look into it, but then I wish I get a recording of this presentation as well. It's a nice one.
Yeah, there is a paper that I can share with Zana and maybe distribute with the participants.
Sure.
Of what we've done in rice, and yeah, it's very interesting. And it's good because the idea is not to start from zero. There's no point to repeat the same mistakes that others like us we've done, for example. So it's just you can start by taking all those lessons and progress, I guess.
Yeah, I can't wait to have the sharing.
Okay.
Okay, thank you. As I can see from the chat session on our Webex link now, yeah, most of the participants give a very nice word. Thank you for your Nice word. Yeah, from Farah Fazril, very colorful slide. From Ling Hao Yi, great presentation to you, Dr. Angelica. From Jenny. And from Kok Zi Hong, very informative presentation. Thank you, Dr. Angelica. And one more question from, I think this is the last question for you, Dr. Angelica. You guys use satellite imaging for collecting data from the field. Do you determine the price with that method too? I think the price of production, I think. So I repeat again the question from Raimi P. You guys use satellite imaging for collecting data from the field. Do you determine the price with that method? Thank you.
Well, we didn't, we did use the satellite imagery to tell us where to go. And we went to the field and collected samples. Okay, we manually did it, all right? In tree crops, it's exactly the same.
All right.
So with the price for the imagery, it depends. As I say, Worldview 3 has a cost of around, it covers 100 square kilometers, so very good area, and it costs between around $7,000 Australian dollars. But Sentinel is free. So with all what we were doing, we test those different systems. So the grower or the industry has the ability to decide which one is better. I hope that respond the question in terms of price. But yeah, we went to the field and collect the samples. That's what we did.
Thank you very much, Dr. Angelica. I think it is answering the question just now. Okay, once again, thank you very much, Dr. Angelica, and to those who threw your questions just now. It was a wonderful session with you, Dr. Angelica. So our second speaker is done, and we are now cannot wait to hear from our third distinguished speaker for Smart Farming International Webinar 2020, which is Professor Dr. Usman Ahmad from Agriculture Institute of Bogor, IPB, Indonesia. So for your information, I have been to IPB Indonesia for a short research attachment in year 2017 at Pak Osman Department, which is the Department of Mechanical and Biosystem Engineering, Faculty of Agriculture Engineering and Technology, IPB, University, Bogor, Indonesia. So before I invited Prof. Osman to give her talk on her topic, so I would like to give a very brief introduction or brief biography of Pak Osman. So Pak Osman is a professor in post-harvest technology and came from the Department of Mechanical and Biosystem Engineering. So the the post that he had before is being a secretary for Center of Research on Engineering Application in Tropical Agriculture, IPB University. He also had being a director for Center for Research and Engineering Application in Tropical Agriculture, and in addition to that, he is the head of Laboratory of Food and Agriculture Product Process Engineering from 2014 until now. At the same time, Prof. Osman also being a leader or a head of Post-Harvest Technology Magister Program, Graduate School, IPB University from 2017 to current, today. Furthermore, Pak Osman or Professor Osman also is an Indonesian Society of Agriculture Engineer Journal Editorial Board. So Pak Osman also a professional member of Indonesian Society of Agriculture Engineer, ISAE, from year 1993 to current. She is a graduate member of Indonesian's Japan Alumni Association, Persada, from year 20 until now. And he is the founder and the professional member of Indonesian Society of Post-Harvest Technology from year 2019 until today. So the most teaching interest of Pak Osman is for basic thermodynamic and heat transfer, food process engineering, post-harvest psychology, and post-harvest technology. Aside from that, he also focusing on image processing application in agriculture. So his research interest is focusing more on, first, post-harvest technology application in tropical agriculture, and the second one, the applications of image processing in post-harvest handling the agriculture product. So what I could say is Pak Osman or Prof. Osman is the man to talk about the post-harvest. Is the expert on the post-harvest. So if I was asked what I could say about Prof. Osman by using 3 words, I would say that by using 3 I's. Professor Osman is inspirational, insightful, and impressive. His significance on post-harvest field is very wonderful. So without further ado, I would like to invite our third and final presenter today, Professor Osman bin Ahmad, to present his topic. Pak Osman will talk about the use of image processing in quality evaluations of agriculture product. The floor is yours, Pak Osman.
Thank you, Dr. Zana, for inviting me to this very nice event. Everybody, Assalamualaikum warahmatullahi wabarakatuh. I'm going to share. Okay. Can you see my presentation?
Yes.
Okay.
Yes, we can see.
Loud and clear.
Okay. What I'm going to share here is to say most of them are the student project. Can be a bachelor or undergraduate student, and also graduate student that doing a final project in my supervision. Of course, this is some of them may be all related to the Indonesian or problem with Indonesia. As a background here, that many post-harvest handling fruits and vegetable in Indonesia is doing manually, labor step, and also time consuming. And on top of that, the result is sometimes not homogeneous for different workers. Will have a different understanding about the product, and also when they work for a long time, they also sometimes give not consistent product, or not consistent result of classification, for example. Even the work is simple, but they still need some knowledge about the product and also skill to do some work. So this also this means needs we need it's necessary to replace the manual work with some equipment or some machine that can perform longer time without changing the perception of the product. That's mean they can give more consistent to compared to the human job. So our student interested in some in this problem and try to solve by using image processing. Well, in the morning, in the first session, Dr. Siti already talked about the revolution, Industrial Revolution 4.0. It is very nice now. You can see everything is available in digital. Compared to the time when I was a student, it's very difficult even to write a program, short program, a short computer program. You need 100 of lines just to perform a small task. Yeah. Now you can do it a very different way. Also at the time, the computer was very low, limited memory that you can cannot do some heavy computing on that. Yeah. Now students interested to give and try to solving the problem. Some of them working on the software development. Yeah. Some of them doing in machine design and construction. Of course, there is also need interfacing platform to use both the software and hardware in order to do the job like you see it done manually right now. Yeah, very interesting that now student student now can find very a variety of camera, yeah, even small one, professional one, with a very powerful gadget, the small form, yeah, very different with the 30 years before, the big computer, but very small in power. So this is interested for the student why they want to try this. Talking about the Industrial 4.0 that already talked by the previous two speakers very well. We can do that only if we do some works automatically, yeah, not manually, because we need to produce some data, and the data is will be feed to the system, and the system do many things to even to make a decision or something else. Yeah. Because we need to try to imitate the human work, we need to imitate also the sensor that used by human. Yeah. As we see that human have a 5 sensor, yeah, from visual, yeah, and also hearing, tasting, and also touching, then smelling. Yeah, this these three type of sensors work very well in technology. It's mean for visual now people can produce or can build a very nice camera. Even if our eyes is only working for from 400 to 700 nanometers, the camera can work even broader than that. Yeah, can be in UV section, it can be in IR, and also in other wavelength. Yeah. so many advantage of this using different kind of camera. Also, the hearing system, we can hear also in this frequency. Some tools can even do in different frequency. Yeah. Touching also, they can produce a small sensor that can measure the pressure, like we do with our with our hand. Yeah. Although for taste and smell is a little bit difficult to build, and now it's not available yet, I think, in the market. Yeah, that people should be develop themselves if they want to use the taste and smell sensor. Yeah. Now we talk about only the sensor that using the camera to learn the object. Here's a student, it's a long time ago, yeah. My student working on a mango, yeah, different type of mango. They see them in the field that mango sorting and grading is doing by based on the color and the size of the mango. So try to learn the mango by image processing to find a useful parameter that can be used for a classification based on what they done manually in the mango packing house, for example. Yeah. We do the real-time image processing. After learning the parameter using still image programming or image processing, we can convert the program to the real-time image processing here. Yeah. So we can directly extract the parameter that we need from the object, from the mango. For example, the area, the color, and other parameter maybe that we need to make a decision what label of this or what category of this mango. Then another student may be working in the machine in construction. Yeah. For example, here that we can see the mango for we have different mango. This is for the aromanis mango. This is for the Gedang Gincu that producing a different color from for different quality. This is almost same color, but has some other parameter to recognize and categorize into A, B, or C, or 1, 2, and anything you can name it. But it's grading. It's grading into some classes. Yeah. This is based on the color and not color. This is based on the shape and size. This is based on the color and size. Yeah. This is to reject the abnormal appearance of the mango. While for everything we do in image processing, we want to separate, or we want to make sure that the first, the superior quality of the mango has the same taste, yeah, has the same quality, but we only guess the inside quality by accessing or by evaluating the outside parameter. This is in this case the shape and the color of the object of the mango. Another student may be working on the construction and designing and construction of the sorting and grading machine like this. Yeah. So this is not one student, another student doing this, another student doing the image processing. So they combine to perform, to try the program into the machine. Of course, and program also they have to do some coding how to control the electrical motor here to move the mango from the feeder to the camera area, and then image processing, doing analysis around here, and then after labeling, the mango can be conveying around this rubber conveyor, and then move to accordingly the quality of the product. If the mango is not one of the quality, not one of the quality categories here, they can be led to the other box. That is mean this is the reject box. It's 1, 2, or 3 qualities around here. Same case also with the citrus. We have a problem also with citrus that the color is and size is mixed when farmers harvest from their child. Although we want to make some of them are in yellow like this, some are still green, and also the size are so different. Some other students also do the same, almost the same with the mango. This is from see the quality of the citrus by size and peel color, also extracting by image processing. After that, they try to compare the classification based on image processing methods of the computer. If they put it in the standard, which one is better, which one is closer to the standard, because when they have a bunch product like this, they have to work, the worker have to work very fast. Sometimes they miss. Sometimes they do wrong classification. That means still mixing between good one and bad one, or premium quality still having the average quality inside. So we try to use image processing also, and some small machine to separate or to categorize the fruits. For example, here to predict the size, you can use this the projection area of the image of the fruits in 2-dimensional. If we do projection the area and we combine, we check with the weight, the real weight of the product, we have almost perfect relationship between area and the weight of the product. That means we can use the area to separate or to categorize or to classify the citrus based on the size. We don't need weight again for doing this one. And the mixed color is very good if we can separate, for example, here. This is just for example. Of course, we can do this based on the needs, market need for this. A1, for example, yellow one. Yeah, this is the same color for a big one. A1, for example, yellow. A2 is green yellow, and A3 is green, mostly green. So we can separate the quality based on the size and color. If the smaller one, we can do it again for B1, B2, and B3. That's really according to the need in the field, what kind of, how many classes the market want to sell the product, or the buyer wants to buy what classes. We can separate. Yeah, this is easy, and this is easy. I mean, we are able to arrange this classification in the program. Yeah, so we in this we do this without seeing the market need, and just this is for the experiment. Let's see here that if we compare the manual the manual working here, just many of them are overlapping. That means one workers may be working good in separation or in classification, but the other workers may be do wrong. So still mix. Yeah. Still mix. That means this what I give sign here is in red circle. It should be in class B, yeah, in B class of the quality, but wrong classification here. This is also wrong classification. Yeah. This is also wrong. Should be B, but considered as C, and so on. By doing the image processing, we can separate them very clearly. A, B, C, almost without overlapping. Yeah, almost without overlapping, because computer works very easy in this case. Yeah. For example, here, after learning the many sample of the fruits, the relationship between the weight of the fruits with the area of the fruits in image, we can do this as input in our program, and then we can see the classification here based on SNI. SNI is Indonesian standard for the product. Yeah, for every product we have the SNI. We can see this all is more than 90%. More than 90% agree to the standard. If we do this by visual, it's very difficult to get this percentage. Yeah? Or if we do with the weight, it will takes very long time. Yeah. So it's difficult to do manually, but with computer you can do once in two category, in two parameters. Yeah. Size and color, you can do it directly in one program that maybe takes only a few or maybe less than 1 second. Here is the example that the manual workers put this many fruits. It's just a example of the manual grading. They put in the class E. That means very small and maybe not suitable to the market. Yeah, according to SNI. Yeah, they don't care about the color. Yeah, for example. So everything here is mixing for good one and bad one, big one, small one. And we do image processing, for example, we can rearrange that. Actually, according to SNI, is not E. They are not reject or not the lowest quality of the fruits of the citrus based on the size, but they are still in C and D class. So we can again rearrange based on the color. We can put them in the same color, yellow, green, and green. Maybe this one can be sell in a little bit higher price than this and this. Also, this one smaller that can be put into D classes, and also still still we can put it in market with even in the lower price. That means that computer can do some correction. In image processing can do some correction to the manual work. The other student also working on how to do it automatically with designing the machine to do this. Yeah, it consists of the belt conveyor. This is the image processing system taking the data image from camera directly, and then real-time processing. and the result is informed to the system again, where the system now can put one by one into the line, the fruits here, and the other result is will be sent to the this is the pneumatic lever that can put the evaluated citrus into the right boxes. Here, the photos of the let me see that constructed by the student. Of course, we need some image processing unit here, computer. This also can control the electrical motor here to move the conveyor belt. So whenever the citrus enter the, what happened? Okay, everything's okay? No?
Okay.
You can something changed in my screen, so I don't. I still have sharing. No.
No, Doctor.
Okay. Sometimes there's
Internet interruption, I think.
yeah, sometimes disturbing with the connection. Yeah.
Yes.
Because
Yes.
nowadays
now we can see your slide.
Okay.
All right,
Because
wonderful.
nowadays many rains in Bogor, in my city,
All right.
disturb the internet connection. Okay, can I continue?
Yeah, sure.
Okay.
The floor is yours.
Here is the component. You can see that the product is divided into 4 classes in combination between size and color. Another project is student wants to learn how to find the ripe melons, because melon here in the garden, in the orchard, is not ripe in the same time. So sometimes the farmer cannot see the difference from the color. They are. So we have a melon with the different tastes, even from coming from the same orchard. The change in color is very little, difficult for human. We try to see here by image processing. This is a simple color extraction from some image. We remove unnecessary thing from the image, and then we improve the shape, and we can only focus on the fruits part of the object, and then we calculate or we extract the color using the RGB and SHI color model. After that, we can see with different 1 week difference of harvest time, we can see that the change in color is gradually consistent. Yeah, if you see the red one is going increasing the color component, the blue one and green one usually will be offset with the red one. And then from HSI color model, we can see the hue is decreasing, but the saturation is increasing. From here also we can see that from the last 2 weeks there is no big difference. That means the melon already ripened after 60 days of planting, and then if we give some more 1 week time, it will change a little bit. So we can harvest here or here. It's no big difference. The student also doing some statistic with the data, and then come up with the idea how to put the program to the smartphone that can be used by anybody to check the melon in the field, and within this time to harvest or not. This is enough quality or sweetness or not to harvest. Another thing is we have a problem with the mangosteen for export. Some exporters said that they can only export the mangosteen with the very nice green and fresh calyx. It's very difficult for them to train the workers which one is good, which one is bad. Sometimes still mixing. So another student try to also working with this mangosteen to differentiate between the export quality and the local market quality, because it needs some time to send to ship the product to the other country. So they need a very, very good shape and freshness like this. In simple image processing, here can recognize only the calyx and then calculate the area with different way to see which one is better to differentiate the calyx area. Here they can recognize the first method can recognize the export quality by 91%. For 240 sample. The second one, after applying the convection to calculate the calyx area, they can increase a little bit to 95%. So this can also be possible to recognize the export quality of the mangosteen by image processing. Another thing we do with the coffee beans is very categorized in coffee beans. The student went to the exporter and asked what kind of beans you want to remove from your coffee, so you have a good coffee for export. This is very a number of beans. So they built the program to recognize the beans and then calculate some features, shape feature, some feature, and then it combined to see which one is good, which one is bad, according to the shape and also color, so we can recognize the defect and separate them into a good export quality, and the other is not good enough for export, because for export is very tight the quality. That's for coffee. This is not food, but also very important in Indonesia. I think also in some country in Thailand and Malaysia, I think they produce rib smoke seed, the natural rubber for anything to sell in international market. They have a quality like this, quality 1, 2, or 3. They do it manually. And Indonesia has some problem back to 2010 or 2011. Some of the quality is not acceptable in the international market because of the maybe not so well training workers cannot differentiate between 1 class, 2 class, and so on. They have to work manually like this, and you can see that many different workers maybe have different experience. Yeah. So try to solve this using image processing, because every pixel in this different quality of RSS is having 3 values at green, red, green, blue. So we can calculate using RGB or using other color model like SHI, but we have to take the picture in backlighting model, yeah, as they do in the fabric. This can do some correction. For example, this is no problem. Yeah, workers and computers agree. This is quality 1. This is quality 2. This is also quality 2, quality 3. There's no problem. But some of the results showing that this should be not 1. Yeah, this is the left one is manual, right one is computer. Should be 2 because what to say, the thickness is not the same like this, not uniform like this. Yeah. This should be some correction from quality 2 to quality 1 because it looks like very nice like this one. Yeah, thickness is homogeneous, and also the color is good. Yeah, yeah. Why it should be put into second grade? Yeah, this should be first grade. This is also a different result from the manual that's saying that second grade, and while computers say this third grade, because some of them this is good in this is not good in natural rubber, and this is not good in the smoking time, smoking process. This is also not so bad, but manual said this is quality 3 or third grade. Computer said the second grade. We can see that image processing can do some correction, and it's, of course, this is they are consistent to do that. What I say, what I show you from first to the 6 is what we do with the product, with what we do with the post-harvest handling. Image processing also can do to control during the growth period of the plant. For example, in greenhouse. We can monitor one of them, and we can treat all of them in the same time. Yeah? Not necessary to control or to learn from every each of the plant, but we take one that can representative because they are planted in the same room, and from the same seed, same environment, and so on. So the idea is, why don't we control only one and then treat them all together? Yeah. This is what we say in our university's fertigation system. When we put the water and nutrition here, yeah. If it's only water, it's no problem to give them many times because water is cheap. But if we put some nutrient here and we give more than they need, that's wasting time, wasting money. Yeah? We cannot do that. So we want to learn from the plant. What they need, when they need the nutrition and water. That's why some people say the speaking plant. So the idea is like, before that we learn the growth period of the tomato with the normal and a little bit different dosage of the nutrition in water. We monitor the growth rate, and then we can see that they are all in normal condition. Even some treatment with the dosage of the nutrition in water. So we developed this system with camera watching on one plant, and then the computer will tell when the pump should be on to give nutrition in water to the plant and also to the entire plant of the in the same greenhouse. This is the idea. It's very simple actually. This is the basic plant speaking system. Only see the freshness of the plant. Yeah, the freshness. The idea is when your plant is need water, they will experience wilting. Wilting means that they are changed different with the position of the every leaves here. Yeah? So ideally, we cannot take this picture outside, because outside maybe there is a wind that can move these leaves, so we cannot compare. We compare. For example, we take you take the picture every 15 minutes to see whether the plant needs water or not. Yeah. Even this is real time. We don't need to take every second or every minute. It's just to close. Yeah, not change. Nothing change between in short time. So take it in 15 minutes and compare. And we analyze this and we calculate everything. Yeah? And then we it is some sample of one data. Every 15 minutes, we calculate the wilt degree in percent, and then wilting gradient. So the degree is changing. And interestingly, during the morning, the degree is negative. The gradient is negative, and that start to wilting process here. Processes, and the condition where the plant is categorized as need water and nutrition is here. Yeah, two combination of this graph. So the rule is wilt degree 2%, and then the previous width is bigger than now, so the pump should be on. Yeah, after pumping, so the condition is changed again to the freshness. This means the plant fresh again. After maybe later it will come up again, then pump again. This can save many nutrition, because the nutrition is not cheap. Yeah? This is the main cause of the production in the greenhouse with the hydroponic system. If we do, for example, if we do the pumping every 30 minutes and every 1 hour, that should be drained out. Yeah? Then this is the wasting. I think that's what I can tell you all. Thank you very much for your attention. I hope this can give some information for you. What we do in IPB, and also you do in your university. Maybe sometime we can share each other and see the one another to improve our work. Thank you very much, Dr. Zana. Thank you.
Thank you very much, Prof. Osman, on your great presentation. Just now on the topic of the use of image processing in quality evaluations of agriculture products. We are impressed with the talking plant just now. A big round of applause to Prof. Osman. Prof, you nailed it. We are so proud with your significant achievement and contributions. Awesome, Prof. And we had witnessed your expertise in post-harvest engineering technology. So with that, is there any question from the floor to Prof. Osman on this topic? Ada soalan? Okay, there is some question here. Muhammad Hafiz Abdul Rahman. Prof, one question for you. Does the imaging technology can be used for any other types of crops? Once again, does this imaging technology can be used for any other crop?
Yeah, thank you for the question. Actually, the image processing is trying to imitate our eyes. Yeah, our eyes. So everything that you can judge with your eyes, it's normally or it's maybe technically can be done also by using camera and image processing. But the complexity is sometimes different. If the manual judgment using eyes is doing by specific or very, very well trained person, it's maybe they use many complex parameters that cannot be quantized. Yeah. Needs some many experience, long experience. We have to build maybe very very complex rule for that. But a simple one only for color or for a shape factor and everything we can do very easy. The key, what you need to remember, keep in mind is how they judge manually, what parameter they use to classify the product. If they use their eyes, probably is very sure that probably we can do it using a camera and image processing. Okay, that's my answer, Dr. Zana.
Yes, thank you very much for your great answer just now. So we got another 2 questions for you. Many participants were interested in this topic, Prof. Okay, I got another question from Odili Obrin Gepitar. So the question is, any thoughts on deploying deep learning method instead of raw image processing? Any thoughts on deploying deep learning method instead of using raw image processing?
Okay. You can combine image processing with any other method. Yeah, image processing is only try to dig up some important parameter from your image. From your image, you can have some parameter, but how you use the parameter, it can be another issue. You can combine image processing with the artificial neural network. You can combine the fuzzy theory. You can combine it with the deep learning, or even any other statistical method like discriminant analysis and so on. So it's different. The image processing is taking the parameter or extracting the parameter, important parameter from the image of the object, while the deep learning is how to use the data. Yeah, like in artificial neural network. I think like that. You can do it. Thank you.
All right. Last but not least, one more question. Can this technology used to evaluate mild symptoms of insidious fruit root, IFR, in mango. Can this technology used to evaluate mild symptoms of insidious fruit rot in mango?
Fruit root?
Yes, insidious fruit rot.
Well, as I said, this is what type of this depend on time camera you use. Yeah, if you use the normal camera that working only from 400 to 70, 100 nanometers, you can see only the surface. Yeah, so what you can judge from the surface, you can do this with the camera, with the normal camera. But if you want to judge beyond that, for example, you want to learn also the composition of the organic matters in mango, maybe the sugar, the acid, and others content in the mango that not reflected directly to the skin color or everything visually. You may have to use the NIR camera or UV camera. That's mean what you can do with the data is depend on the kind of the data and what you can get the data that's defined of the what type of camera you use. That's I answer this generally because I don't understand so much about the case you're trying to ask me. That's depend on the hardware, on the camera sensor. This is kind of sensor. Yeah, thank you.
We got the line problem just now. Sorry about that. Okay, anyhow, it was a very great reply from Prof. Osman. Thank you very much for your answer session as well as your presentations. So with that, Mark, our session today will end soon. And thank you for our three distinguished speakers, which is Associate Professor Dr. Siti Khairuniza Bejo from UPM Serdang. Our second presenter, our second speaker is Dr. Angelica Suarez from University of New England, Australia, as well as our last but not least, Professor Dr. Usman Awang from Institute of Agriculture Institute of Bogor, Indonesia. Both of you, not three of you, did a very, very, very good job. Wonderful. Thanks for joining us. Bina, thank you very much for your great support and time in order to be with us today. Even if it is a very weekend moment, those who love to stay and relax at home, but you spend your precious time with us. It is a great support from the MSE as well. And I would like to thank our Secretariat of Malaysian Society of Agriculture and Food Engineers Student Chapter UPM Bengkulu as well, because without them, this webinar will not be happen today. Thanks again to everyone, and thanks to those who already registered and participated this morning, starting from 8 a.m. in the morning until now. So currently we got more than 400 participants in the WebEx list. Well done, everyone. Thank you. Thank you for your time, and thank you for your focus and concentration. With that, I hand over the session to our MC, Mr. Gabriel, to say something to you guys. Thank you very much. With that, Assalamualaikum and Salam. We love UPM.
Waalaikumsalam. Thank you.
Thank you again to Dr. Wan as our moderator for today, and also to our three speakers, Associate Professor Dr. Siti Khairuniza Bejo from UPM Sedang campus, Professor Dr. Usman Ahmad from IPB Indonesia, and also Dr. Luz Angelica Suarez from University of New England, Australia. Thank you for the great sharing of information. It was very precise and relevant. I am sure all of us in this room can relate to each other and every word that you mentioned. Thank you for sharing. And finally, ladies and gentlemen, to all the participants, I hope you have found this morning talk informative and useful. Thank you for spending time with us today. Fortunately, some of the participants who can't join us today due to some technical error or network error, but no worries. We will upload this meeting in the YouTube and we'll blast the link via WhatsApp and also share the presentation material in WhatsApp as well. So that's all for today. Thank you for joining us and have a nice weekend, everyone.
Thank you, everyone. Congrats to the organizer.
Thank you.
Thanks to
Thank
the
you.
organizer, yeah? All right.
Yes.
Okay.
Thank you.
Bye.
Have a great weekend.
Thank you. I
Bye, Angelica. I miss you.
miss you too.